We will see that the ocean is got this nicely stratified structure. We already saw the mixed layer as the region where we have isothermal and isohaline conditions in the vertical because of the turbulence generated by the winds and the heating and the cooling. And it's stratified in the interior from the thermocline to the deep ocean. So the question is then, if the layers below the mixed layer are isopycnals, then how is that communication happening between the mixed layer, where the density is being generated by the mixing processes and the turbulence, and then they are injected into the interior. So I will use a couple of figures to explain it before we go on to the physics in terms of the mathematical equations. Looking here at the ocean, going from the bottom, let's say minus h, to some depth d0 where the ocean has a level of no motion. So if you go deep in the ocean, the waters move so slowly that you cannot directly measure them at all. So they are moving, but essentially they are at rest compared to the time scales we are worried about, even at decadal, multi-decadal time scales, which means that the pressure gradient has to go to zero at some level as well. So this is shown here as dp dx and dp dy equal to zero, with the geostrophic currents and the vertical motion going to zero as well. And as you go to the surface layer, you have some depth at which the wind stress effects do not penetrate to that level. So the tau x and tau y go to zero, and that's where the effective forcing of the winds generates the vertical velocity, which we will see as known as Ekman pumping or Ekman suction, so convergence and downwelling or upwelling. So that's written here as W equal to WE. And at the surface you have the wind stresses which we wrote as rho 0 AZ times DUE DZ, and rho 0 AZ dVE dZ as tau y, and we said the surface currents are going to be the sum of these Ekman currents and geostrophic currents. How does that work? Essentially, wind, let's say on the equator, the southeasterly trades and the northeasterly trades blow across the equator, and Coriolis is pushing to the right in the northern hemisphere, to the left in the southern hemisphere. So you have a divergence right at the equator, and water is brought up. There is an upwelling. So you can have isotherms or isopycnals doming up, and if the pressure at some level has to become flat, then the sea level has to drop. So essentially you have a compensation happening of the isopycnals dipping down and the sea surface height dipping up or bulging out, and the isopycnals doming up like shown here, and the sea level having to dip down. Okay, that's kind of heuristically arguing. We will see that a little bit later on. So in the interior, this Ekman pumping or suction is received, and the interior adjusts to geostrophy again, where we are writing F times Ug equals minus 1 over rho dp 1 over rho 0 dp dy, remembering we are doing this Boussinesq approximation, and Fvg equals 1 over rho 0 dp dx. So the interior pressure gradients are set up in this simple situation by the wind stress forcing, and the doming up or down of the isopycnals produces the horizontal pressure gradients to which you have geostrophic adjustment and geostrophic currents, right? The situation is not that simple, because if the interior is stratified, then how is it that the turbulently mixed densities at the surface are adjusting to the isopycnal that is meeting the bottom of the mixed layer? So there are many details that we will not talk about. This is a figure from Jeff Vallis's book, which is much more detailed about the geophysical fluid dynamics issues associated with that. So ocean has this kind of structure where you have at the equator wind pulling up the isotherms and upwelling happening, and you have the polar regions where cooling and cold waters are sinking right to the bottom or the intermediate depths, depending on how heavy the water is. So there is a direct communication of the thermocline here with the atmosphere, whereas at these intermediate stages there is some sort of a communication happening. Here you can see this well mixed layer matching the interior, and there you have the Ekman layer creating a convergence and pumping of fluid into the interior. So these are quite complicated thermocline theories that we will not get into, and we will also not get into the subtropical gyre in too much detail, because that's on the edge of the low latitudes that we are going to look at. But you are probably already exposed to some of this. Here is the equatorial or the low latitude region, and there is the mid latitude. So you have mid latitude westerlies blowing the ocean from west to east, whereas you have trade winds in the lower latitudes, subtropics and lower towards the equator, pushing the water westward. And we know that the Coriolis is going to push this to the right or southward, and Coriolis is higher at these latitudes than at the lower latitudes, where the trade winds are pushing the water to the west and the Coriolis is tilting to the north. So there is more water coming to the south than being pushed to the north. So there is a bulging in the middle, and that's shown here as the dome that is formed by Ekman transports. And there is a convergence because water is coming south here, going north here. They are meeting in the middle. Thermocline is being pushed down, which means the surface is doming up. And you have gravitational flow down the dome. Coriolis acting on it and producing geostrophic currents. And then there are weak eastern boundary currents and the narrow, deep, fast western boundary currents, which are related to balancing the vorticity that is put in by the winds and to balance the mass that is being pushed by this wind stress curl. Wind stress curl is basically the curl tau that's induced by winds being westerly here and northeasterly here. So you can curl your fingers around the winds and it points downward, which means the vorticity being put into the ocean is negative. So somewhere you have to produce positive vorticity, and it turns out that you can only do that on the western boundary. So the main reason why you have this strong, narrow, deep western boundary current is that you have Coriolis increasing with latitude, or what we called the beta effect, the DFDY effect. Okay, so that's the brief explanation of how the Ekman currents and the Ekman layer are going to meet the interior ocean. When we look at further details mathematically, we will derive the expression for this Ekman pumping and look at how that sets up the interior flow and what patterns emerge because of this wind stress curl and interior transport integrated in the vertical. Okay, interesting solutions emerge, much more simple compared to the atmosphere that we have been discussing in terms of setting up the tropical dynamical circulation in terms of vorticity stretching, heating because of the condensation, etc.